For today, we will be going through the chapter of metals, and these are the segment. This is actually going to be a very long segment where we will be touching about reactivity series, how to go about using the reactivity series. So usually questions like this will appear in the form of a table, and from the different properties given to you or observations, then you'll be required to identify the which metal is actually more reactive than the other in the questions. So these tend to appear in MCQ as well as the structure. Next, we look at extraction of metals and use of steel. So this one will come in more for let's say for science chemistry, right? It will be the equations, and then you'll be required to list the steps on how iron ore is actually extracted from hematite. Okay, and of course, use of steels, rusting, and recycling metals. Recycling metals can come in through open-ended kind of questions where you'll be asked why do we want to conserve, what are the benefits, what are the some of the disadvantage. So when we look at metals, right, we look at the physical properties of metals. So metals tends to have actually good conductors of heat and electricity, and when we say good conductors of heat and electricity, means electricity is able to pass through, and at the same time current is able to pass through. The reason for this is because at the atomic level, right, the particles have the metals actually are surrounded by a sea of delocalized electrons that helps to actually carry the electrical charges. Yeah. So around it, you have the sea of delocalized electrons, and these electrons will carry the electrical charge. Hence, it is able to be a good conductor of electricity. They have high density, meaning, right, what we'll do is it tends to sink in water. Generally, why? Because metals have a higher density than water. There are of course a few exceptions, but I would say it has a higher density. We tend to say that maybe the mass is greater as compared to the volume. So next is the melting point and boiling point is also high, which means that it takes a lot of heat energy required to actually overcome the forces of attraction or the metallic bonding so as to change from one state to another. Malleable meaning when you bend it, it doesn't actually break easily. So this is without bending, without breaking. And of course, ductile means you pull like spaghetti, you pull it, you stretch it, it will also not break. So these are some examples of the physical properties of metal. So this is a key exam question in which they always ask why do you want to actually make an alloy and what's the difference. Because pure metal tends to be very soft at its pure form. In a way, if you remember in kinetic particle theory, the particles are always arranged in a regular arrangement, and this regular arrangement allows the atoms to actually slide easily over one another when a force is applied. Whereas for pure metal, they tend to react with air and water, and thus actually wear away or corrodes easily. So this is what we call rusting. But on the other hand, if let's say, right, you introduce an alloy is actually a mixture of metals with one or a few other elements. That means having a pure metal, you add in another element, what will happen to the arrangement, and what can this will actually lead to a difference in terms of physical properties. So the reason why we want to make alloys is to actually make it harder and stronger. So one very important alloy that you have to remember is brass, which is made of copper and zinc. This you have to remember. This tends to be harder and stronger than pure zinc. Sometimes it can also be used to improve the appearance of the metal. So for example, if we look at tin is very brown, very kind of metallic kind of or boring color. Whereas for pewter, which is an alloy of tin, antimony and copper, they tend to give a very shiny feel. So that helps to improve the appearance of metals. So sometimes you want to also lower the melting point of metals to do soldering. Soldering is something like you want to connect wires together, you want to connect metals together. So generally, solder is actually an alloy of tin and lead, and it has a lower melting point than pure tin or lead, and generally it's used for joining of metals, like a wiring. Sometimes, of course, you also use it to make it more resistant from corrosion or rusting, like your coins. Now coins, you do not want it to be able to rust and then you devalue it, or dissolve in water, that kind of thing. So one of it is using this particular alloy where it's a mixture of copper and nickel, so as to make the coins actually very strong and in a way rust resistance or corrosion resistance. So how then in a structural form it's made is that for alloy, right, it's generally harder and stronger than pure metals, as atoms of different elements, right, will have different sizes. And in this case, when you look at the brass, they are made of two different types of metal. They tend to be inserted into the alloy, into the arrangement, such as this will actually tend to disrupt the orderly arrangement of the atoms. This disruption will then cause the layers of atoms not being able to slide over each other easily when you apply a force. Hence, it makes it very hard and strong. Of course, these are examples of alloys which you don't have to remember the percentages, but it is important to know the compositions, like what are the elements that make up for and what is it used for. Some general special properties can be remembered to help you to better understand what are some of the uses for it. Next, we move into the reactivity series. Now for reactivity series, you need to actually remember the order of the reactivity series. So in the reactivity series, metals are usually arranged from the most reactive to the least reactive. Then how do we compare reactivity series is whether it's able to react with cold water. Steam is actually hot water in this case. And then of course with dilute hydrochloric acid. If the metal is very reactive already, then it is able to actually just react with water, cold water. However, a more unreactive metal, you will need a stronger reactant to cause a reaction, and therefore you will use an acid, a hydrochloric acid. So if I were to draw an arrow of cold water, hot water, and of course acid, the least reactive acid will be here. And then the most reactive, sorry, not acid, but metal. And the most reactive will be at the top. Of course, if you are already so reactive, right, then you definitely can react with an acid. So generally, these are some of the items to take note of. So when we look at reaction with cold water, this is important, where you need to know the word equation, where metals when react with cold water, they tend to form metal hydroxide. Metal hydroxide is basically the metal with, let's say X is the metal, so when the cold water, it will actually form a metal hydroxide, something that is OH plus hydrogen gas. So this metal hydroxide tends to be an alkali. So in terms of universal indicator, it will become more violet in color or purple. Hydrogen gas will then relight, extinguish, with a pop sound on a lighted splint. Lighted splint. Okay, so for potassium, they tend to be very violent. In terms of when you actually react the potassium metal with water, cold water, and it's highly exothermic. Highly exothermic means that heat is generally released. And what you will see is that the temperature would actually increase. Okay, and it will explode with a lilac flame, the hydrogen gas. Sometimes in exam, you might be required to describe the observation and give the chemical equation. Sodium, the next reactive metal below of potassium, it tends to react very violently and highly exothermic, and of course the flame burn is actually yellow in color. But you do see that each of them actually forms a hydroxide. It's a base. Then you have calcium, and that reacts with cold water, but one thing to take note is this reactivity tends to go down already. So you can see from react very violently, it moves towards reacts readily and then reacts slowly. And definitely as you go down the reactivity series, the reaction between zinc, iron, lead and copper, silver tends to be actually unreactive. Why? Because these metals, they tend to be actually least reactive. So using cold water is not sufficient to react with them. So what is next is to actually consider a more heavier substitute, which is steam, which is hot water. And you can see that with hot water, right, even though the whole thing is different, you actually form an oxide, meaning the metal is actually with an O, matched with an O. So of course it can be O2, dioxide and what's not, depending on the charge of the metal itself. Okay, but you'll still be able to release hydrogen gas. So this is a way, one way where we can actually collect the gas. Of course, we use hydrogen because it's an insoluble gas, so we use displacement of water in this case. Of course, to prevent water from being sucked back into the hot test tube, the delivery tube must be removed from the water in the trough before turning off the Bunsen burner. Okay, because if you switch off the Bunsen burner first, this will cause a cooling effect such that air will actually go back into the to the test tube here, then you suck the water in. Okay, so what is pushing the force now is because air is produced, it is then traveling down the delivery tube and up here. So it gives a pushing force in this case. Next, we look at the reaction with steam. So for reaction with steam, right, the magnesium tends to react violently to produce a white glow, whereas for zinc, it reacts readily. While zinc oxide form is actually yellow when hot or white when cold. Iron reacts slowly, and of course there's no reaction for these three in hot water. Then some of you may ask, well, potassium, potassium, sodium and what's not, they are all actually the same as what you react with cold water. So same, just that the equation will be different. Next, we look at the second tier, which is the acid. So this one we have learned in acid and base chapter, such that metals when we dilute hydrochloric acid, it will form metal chloride plus hydrogen gas. So metal chloride here is something with Cl, so something Cl, and this Cl comes from the hydrochloric acid, which is the HCl. Of course, you will still be able to form your hydrogen gas. Again, the number of chloride will depend on the charge of the metal itself. But you could see that for potassium, sodium, calcium and magnesium, they tend to react explosively, if not violently and rapidly. Okay, however, if you look at the rest, you have your zinc and iron still able to react, but there is no reaction with lead, copper and silver. Why? Because lead, copper and silver tend to be very unreactive, even with metal. Okay, lead on the other hand, when they actually react with acid, right, it can actually form some form of insoluble layers that it doesn't allow it to be soluble to allow that metal to further react with the acid around it, so the reaction will stop. So how to go about remembering all the reactions based on the reactivity series? We use this potassium, sodium, calcium, magnesium, zinc, iron, lead, hydrocarbon, hydrogen, copper and silver. This is very important and is tested in exam, where you are not required to list, but you might be required to, based on this order, to give certain interpretation of the observation. Okay, the reason why, even though lead is more reactive than hydrogen, it shows very little or no reaction. Reason being is like what I shared, because it forms an insoluble layer around the lead, further preventing the lead from reacting with more hydrochloric acid. Hence, there is no reaction or minimal reaction. Okay, so these are also the ones in terms of comparison of how the different metals will react in terms of cold water, hot water and also acid. So all this we have went through already. Now, how do we go about using the reactivity series? Metals tends to actually lose electrons to form positive ions, and that this reactivity of a metal is related to its tendency to form positive ions. So what happens here is, as you can see, metals are either your group 1, 2 or group 3. And group 1 means you tend to lose 1 electron to achieve the noble gas configuration. Group 2, 2 electrons, 3 electrons. So how easy it is for it to lose all these electrons to form the positive ions depends on its reactivity. So having a more reactive metal, you'll have an easier or greater tendency to be able to form positive ions. In other words, you'll be able to lose the electrons more easily. compared to a least reactive metal. So if we were to write an equation like this, we'll see that let's say magnesium is able to lose 2 electrons less readily compared to potassium. It's not about the number of electrons, like 2 or 1, but rather it's how easy it is to actually release even 1 electron. And this is because magnesium does not actually react as violently with potassium, as it has a lower reactivity as compared to potassium. So these are some of the items where next we look into displacement. So now we already know the order of the reactivity. Having a more reactive metal, you can help to displace a less reactive metal from its salt solution. Okay, and generally this can actually help if we add iron filling to a solution of copper 2 sulfate. So we see iron, right, being of a higher reactivity series than copper 2. So what will happen is this iron will displace copper 2, okay, such that copper 2 will come out and iron will come in to replace the copper 2. So you'll form iron 2 sulfate, and you also form the blue you will form a copper solution. So what we can see here is iron is more reactive than copper. As it is above copper in the reactivity series, therefore iron can displace copper from copper 2 sulfate solution. But if we use what happens if we add iron fouling to the copper 2 sulfate solution? So this is what we'll see lah. Because copper metal is extracted out, right, it got displaced out, right, so it will actually precipitate as a reddish brown solid, while the solution will turn green due to the iron 2 ions, or more specifically the iron 2 sulfate solution. However, if we flip the question, we say that now we use copper to put into iron 2 sulfate. Now, will there be any reaction? There will not be any reaction, because copper is less reactive than iron as compared when you look at the reactivity series, and therefore it will not be able to displace iron from its salt solution. Metal displacement reaction, then redox reaction. So redox reaction are reactions that undergo oxidation and reduction at the same time. So this one, please go and check the other YouTube lessons we have already of the chapter oxidation and reduction. So in this case, right, we would see that the iron, right, is being oxidized to form Fe2 plus because it forms with the sulfate ions. Whereas for copper, on the other hand, the copper 2 plus, please don't write like this, it's actually Cu2 plus. Okay, it forms into a copper solid. So we could see that the oxidation state from 2 plus, it became 0. As for iron, it will be from 0 to 2 plus. So yes, there is a redox reaction due to this change in oxidation state, and where one is reduction, one is oxidized. So reaction between a metal and its oxide of another metal. So oxides of another metal, if we look back at the acid and base chapter, we realize that there are 4 types of metal oxides. Actually 2 types lah. You have your metal oxides, you have your non-metal oxides, we have the amphoteric oxides and the neutral oxide. This really depends on which of the periodic table are we looking at, and that a more reactive metal will generally be able to reduce the oxide of a less reactive metal. So for example, the magnesium ribbon acts as a fuse, and when the magnesium ribbon is ignited, that means we light it with fire, it helps to provide energy to start the reaction between zinc and copper 2 oxide to form zinc oxide and copper. This is because zinc is generally more reactive than copper, and it's able to form the the zinc ions more readily, whereas copper 2 oxide is then generally reduced to copper. We can also reduce the reduction of metal oxides with carbon, but this really depends on where carbon is in the positioning of the reactivity series. So oxides of some metals can be reduced to their metals by heating it with carbon. And of course, the more reactive a metal is, the more difficult it is to reduce its oxide to the metal by carbon. So again, this reaction is very important for the extraction of some of the metals from ores, which we will talk about later. But do take note that for metals that are of higher reactivity than carbon, you cannot use carbon to displace it or to reduce it. Rather, if you still need the extraction, you can use electrolysis, a more powerful way. We can also reduction of metal oxides with hydrogen. Again, it depends on where hydrogen is in the reactivity series. So what is then the comparison between carbon and hydrogen? It's based on the availability of the reactants that you have. So for example, the oxides of some metals can be reduced to their metals generally by heating with the hydrogen. So another one is of course heat on the metal carbonate, where copper 2 carbonate, when you heat it, it will form copper 2 oxides and carbon dioxide gas. Now this one is very subjective because sometimes some of these carbonate, they decompose very easily. So exposing it to direct heating or heat, you can decompose it and therefore damage it. So not all carbonates, like what I say, can be decomposed by heat. And having a more reactive the metal, it's more actually difficult for it to decompose its carbonate by heat. Sodium and potassium are heat stable and do not decompose on prolonged heating. So the other way is also true, where having very stable or very least reactive, a very reactive metal, they tends to be very heat stable as well. Being heat stable, you prolong heating or direct heating, you will not decompose it at all. So one example of a question that can come out is something like this, where you are given 3 different setups, and these 3 different setups, they will also tell you what is being displaced from what solution, and from this you must be able to deduce the order of the reactivity of the metal. So when we see P is displaced from the salt solution, so what we can say is this is S and P, right? So you tend to actually write like an arrow where this is the most reactive, and then the least reactive is here lah. So if S is able to displace P, so means S must be of course more reactive than P. Then when we look at here, Q is being displaced from the salt solution, means P must be more reactive than Q. So this will become here lah, where Q is lower. Then you have metal Q, and R is displaced from the salt solution. That means Q can displace R, then of course R would be the least reactive. So it's SPQR is the order of the reactivity series, where S is the most reactive and R is the least reactive. Next, we will look into the extraction of metals, which is one of the common exam questions for science chemistry, especially for N-level one. So you will need to know this whole section. So what actually it is that for metals, right, they tend to be 2 different kind of states, the uncombined state and the combined state. So the uncombined state, right, will generally mean that you get it from the raw kind of point of view. And this unreactive metal is generally when you go extraction or mining, you'll be able to actually get it. So you have gold, you have platinum and silver. So they are usually there in the raw form. Whereas for the combined state, it's where it doesn't just contain the metal, but also a lot of other materials or mineral ores like metal oxides, metal sulfides, carbonates, and chlorides. So there are some ways to extract these metals from its original ore, okay, which is by reduction with carbon, depending again on where its reactivity positioning is with respect to carbon, and heating the metal with basically carbon. The next one we look at is actually electrolysis, to pass electricity to decompose the molten metal compound and then of course to extract it. So generally this is one order that we tend to use. I'm so sorry that it's a bit out of place, but generally some of these are the items where you would see that the trend, right, is that electrolysis is used to extract metals that are of higher reactivity in series, whereas carbonate carbon is the one below. Of course, ochre uncombined naturally tends to be this one here lah, your silver and gold, where it's usually there in the raw form. So this is the key one where you need to know the extraction of iron tends to be extracted from hematite in a blast furnace, and more importantly the ore of the iron. So it's composed of mainly a lot of iron trioxide and sand impurities, which is silicon dioxide. So in order to extract this from the ore, we tend to actually use a blast furnace. This is actually a very tall chimney light that is made of many bricks, and it has a lot of refractory materials that helps to actually trap the heat. So where do we usually put the raw materials? We tend to put it at the top, the hematite, the coke is also carbon, then of course the limestone. Oxygen or hot air will be given from this area here, as we are doing a lot of heating and combusting, and therefore you will need a lot of oxygen. Slag and molten iron. So molten iron is the one that we actually want to collect, whereas slag is the other impurity. So there's actually 4 main steps in this chemical reaction in the blast furnace. First, we to produce the carbon dioxide. The purpose of this carbon dioxide production is in order to produce carbon monoxide, which helps to actually reduce the hematite to form iron, and of course the removal of impurities finally. So first step is how do we produce carbon dioxide? In this case, you will need to memorize the chemical equation. So first, coke helps to burn in hot air, and this will actually form heat. So carbon dioxide is also produced such that carbon, when react with oxygen, will form CO2. So carbon plus oxygen. Okay, and that this generally, because a lot of heat is produced, is exothermic, and this can be seen where the temperature of the furnace will increase to over 1600 degrees Celsius. Of course, we also have the production of carbon monoxide, where carbon monoxide further reacts with hot coke, and this carbon dioxide will then be reduced by more coke to form carbon monoxide. So this reaction is actually called a reduction reaction. So you can see that the same material has always been revolving around carbon and oxygen. Then finally, we will actually use the reduction of iron oxide from your hematite. So carbon monoxide will reduce your iron oxide to form your molten iron. So what will happen is this thing is your molten iron. So it will actually sink to the bottom of the furnace and known as cast iron. On the other hand, your carbon dioxide would actually escape as hot gas through the top of the furnace together with your nitrogen gas and of course carbon monoxide. So it's if written properly, it's like this. Okay, it's not CO2, it's carbon monoxide. This is a common mistake. It's one of the byproduct is CO2. So you can see that we do have no wastage, where carbon dioxide, when formed, goes back to step 2, whereby it can be used to form more carbon monoxide again by just adding more coke. Then finally is the removal of impurities. There is 2 main chemical equations for this. First of all, limestone consists of calcium carbonate that decompose at high temperature. So you have your carbon dioxide and calcium oxide being formed from your limestone. So this is the first chemical equation for removal of impurities. So once you have your calcium oxide and carbon dioxide, you can see carbon dioxide can go back to form carbon monoxide in the second step again. That's why they use limestone. So what will happen to this calcium oxide? This calcium oxide will then be used to actually extract that silicon dioxide to form calcium silicate, which is slag. So it's a CaO, and react with your silicon dioxide, which is sand in a way, CaSiO3, which is slag. Now, so what is the purpose of this? So what we can see is this slag, right, is actually, it will sink, but it's also being less dense than iron, therefore it will float on top of the iron. So this is important because sometimes in exam they ask the relative positioning of where the different iron or your slag is being extracted from. Okay, So this generally comes out as the whole equation that you will need to remember. Next, we look at the uses of steel. So one example is that steel is an alloy of iron with carbon and other metals. So steel is made from casting the iron from two main stages. Number one, removal of impurities by oxidation. The second one is to actually mix the carbon and other elements to make various types of steel. There are many different kinds of steel, and that this really varies based on the properties of the steel by the amounts of carbon and other metals being added towards it. Now these are a few that you need to know. Number one, we have the mild steel that is low in carbon, but they are strong but malleable. So generally we use it for car bodies and machinery. Whereas for high carbon steel, these tend to be very strong but brittle. You know, like your bicycle, sometimes you use this kind of high carbon steel, and it's light, but at the same time it's actually very brittle but strong. So these have to be handled with care because they can break easily in some sense. Okay, you have your manganese steel and of course your stainless steel. These are quite commonly found. I mean, quite straightforward. Okay, next we look at rusting. Now rusting is the other component that in exam they tend to ask. So rusting is actually an oxidation reaction where it's due to the corrosion of iron, and this gradual oxidation of iron tends to form hydrated iron oxide. Hydrated generally means wet or contain water. So definitely in equation you don't really have to write this H2O because it's not that important, but the rest is quite important. Where iron, when we add with oxygen, you'll form water, and of course hydrated, it will not form water actually. You will need water and oxygen to form rusting. So rust is this reddish brown substance. Okay, of course some other conditions can also speed up rusting, like your sodium chloride or acidic solution. Sodium chloride can come in the form of your sea environment, like go on to a ship and what's not. Then of course acidic is acid rain and what's not. So what will happen over a week for all these test tube? You could see that for test tube A, right, you have this layer of oil. This oil tends to prevent oxygen to react with the nails, and so the nails will actually have water only. There will not be any rusting, no rusting. Because for rusting to occur, you need oxygen and water. Next, we have anhydrous calcium chloride that absorbs water. So in this case, we have no water here, so no water. Down here is no oxygen. So if you have no water, of course down here why they say prevent water is mainly because they want to some water vapor in the air. Then why you boil the distilled water is because by boiling the distilled water, you tend to remove the air in the water as well. So if there is no water, there will not be any rusting, so no rusting. For test tube C, you have both air or mainly oxygen, and you also have water. Therefore, rusting will happen. So even though you boil the water, it doesn't matter because they are still around and mixed. Then of course, you have now salt. So you speed up rusting. So it's like rusting, but faster. Because you have an added agent which is sodium chloride. So you have oxygen, you have water, and now you have sodium chloride. So D will be the fastest, followed by C. In terms of speed of rusting, A and B, there will not be any rusting at all. Some ways to prevent rusting, right, is like using a protective layer by covering the metal. You paint it, you grease it, plastic or whatever you do it. It helps to prevent the contact of your air with the metal itself. So you actually want to exclude either water or oxygen. Why water? Because let's say you're in the boat, you paint it to form this physical barrier between the water of the boat, the water of the sea, as well as the metal of the boat. Sacrificial method is where you want to actually use a more reactive metal, so that metal will get reacted to with water and oxygen first, so rusting will happen first and not touch the other one. This is quite expensive because you have to find a metal that is more reactive than the metal that you use to build your whatever equipment. Okay, then finally there is the use of alloys, where we introduce different types of elements inside it to cause it to be more rust resistant, like a stainless steel. So like what I say, for protective layer, there is the painting, greasing, electroplating, okay, plastic coating to prevent any exposure to water and oxygen. Electroplating is where we pass electricity to cause the other materials to move to the other side. So for example, you have your gold to do gold coating and whatnot. So these are some examples. Then of course, using a sacrificial method, in this case where a more reactive metal, usually zinc or magnesium, will corrode instead of iron in steel. This one, right, is tend to be quite expensive, and you have to do a lot of maintenance to replace the sacrificial metal. Then of course, your stainless steel for your utensils. And now we move into recycling. So a question that they always like to ask is, why do we need to recycle, or why we need to do certain things to reduce the use of metals? It's because the key word for all answers they are looking for is the word finite. So this one please remember for exam. Where metals are finite resources. So being finite resources, right, they will tend to be limited, non-renewable. In other words, they will run out in a matter of time. Or the time for it to actually be replaced is more than the time that we actually use to use the items. Okay, so the world reserve of raw materials may actually last longer if we tend to reduce, which is, for example, to find substitute instead of using metal. Then we can also recycle through crushing and melting of metals to reorganize it for other uses. So these are some of the commonly recycled metals. Like you have your iron and steel from scrap metals, you remelt it to form your metal plates and what's not. Aluminium from your food and drink cans, so that it can be actually recasted to other cans. Okay, lead is usually recovered from your car batteries, so that it can be reused again. And some of the advantages of actually recycling metals is that recycling helps to conserve the natural resources. Recycling also helps to reduce environmental issues or problems that's caused by the extraction of metals. Recycling can also save costs of extracting metals that can be quite costly. Like let's say your hematite, right, your iron extraction for hematite, it's actually a very expensive process because you have to spend a lot of money to build the infrastructure to withstand the high temperature and so on. Recycling sometimes, on the other hand, can also be more expensive than extracting the metals directly themselves. This can be due to the cost of collecting it, sorting, separating it, cleaning it, or even to transport it. There are also some social issues of recycling metals, where recycling helps to provide less waste and of course pose less danger to human health. There is less mining, more land can help to cope with the increasing world population. The effort and time needed to educate this on the community and business to practice recycling is also a way of life or very important. Sometimes in terms of environment, recycling can cause pollution problems. Like for example, by recycling your lead from car batteries, it will be releasing harmful gas to the environment. Okay, so that is all for this particular chapter of matter that we have gone through. It's a very wide kind of thing, whereby you could see that we went through number one, we talk about the structure of metals and how the structure of having an alloy disrupts the regular arrangement to make it stronger. We will follow up with talking about the reactivity series of how the individual order is being done. Okay, so if we were to refer back to I think that's this so this is the one. So what we can see is the occurring naturally cuts off at gold. Okay, then of course from magnesium, until potassium is electrolysis, then of course zinc to silver is carbon. this is for extraction. There is also the part where we can differentiate it by reactivity with cold water, steam, and acid. And of course, with cold water, you will produce your metal hydroxide. With hot water or steam, you will actually produce your metal oxide. And finally, with your acid, depending on which acid you use, let's say you use hydrochloric acid, you will form a chloride. If you use sulfuric acid, you will form a metal sulfate. If you use nitric acid, you will form a metal nitrate. Then moving on, we actually study one case study of the extraction of iron from your hematite. So that one, there's generally 4 steps, but there's a total of 5 chemical equations. Production of production of carbon dioxide. Then you form production of your carbon monoxide. Carbon monoxide is used for the reduction to extract your molten iron from your hematite. Then of course you want to remove the impurity by adding your limestone. Then the limestone will form your calcium oxide, where calcium oxide and also of course your carbon dioxide but calcium oxide is then used to react with your silicon dioxide to form your slick. Okay, then next we move into the concept of rusting, how to prevent rusting, the uses of steel, and finally the importance of recycling metal. Okay, so that will come to the end of this whole chapter of metals.